Good evening, everybody. Welcome back to another Let's Calc video in the series focusing on the Term 1 Calculus AB problem sets. In this video, we're going to focus on the problem set that centers itself around the first derivative test, and boiling that skill down, what we're really talking about is how to determine if a function is increasing or decreasing without visually inspecting a function graphed on a graphing calculator. And then we're going to look at how we can use that information about the function's derivative to determine whether or not we have a relative maximum, relative minimum, or neither at that particular point. So with that in mind, without further ado, let's jump in, try to make the most of the time that we do have. Okay, the first question we're going to... Siri was recording that the whole time. The first problem that we are going to look at comes from the first section, which is just based on visually identifying where a function is increasing or decreasing, but the instructions here are instructive, naturally. They tell us to state the intervals on which each f of x graph below is strictly increasing and strictly decreasing, respectively. So the key word is the one that's underlined, strangely enough, just one time, in looking at this graph. We're talking about something where a function is strictly increasing. And let me first talk about that for just a second. Like, what is the difference? So if we want to talk about the definition of just plain old increasing, like whether or not the function is increasing versus whether or not a function is strictly increasing. Okay, so I'll write these all in here. So that extra adverb, strictly, possibly adjective, whatever. So if we're talking about some function f of x, then we've got one of these two possibilities. Well, our definition using calculus, our calculus-based definition of f of x is increasing, is defined using the derivative as that f prime of x is greater than or equal to 0. So with straight up increasing, just plain increasing, what they mean is that the derivative is either positive or 0. Or more specifically, f prime is non-negative, would be the cleanest way to do it. That is the most formal or very common formal definition of increasing. On the flip side, if we talk about strictly increasing, that's more or less what we've always considered to be increasing before. That means that f prime of x is literally positive. So we're talking about a positive derivative, not just one that isn't negative. And so what happens is when you do it this way, you get slightly different intervals. Like what happens is we either include or disclude the 0 part, the place where the slope of the function is 0. And there are other little cases that pop in there. For this particular problem, now that we've kind of clarified those pieces, I want to start by focusing on the two things we were asked for. We were asked for strictly increasing and strictly decreasing for this function. So in looking here, if we start things off, we have to write the word strictly increasing. And then we're looking for the x values on which this applies. Now in our picture, there's some things to note here. First, the implication of this picture right here, I don't know if you can see that I'm drawing over the function. The implication right there is that we have a particular type of non-differentiable point there. In fact, the implication here, what I'm hoping you could read from this picture, is that we have a vertical tangent line. So that is a place where f prime of x goes to infinity, but more importantly, f prime of x does not exist. So the reason I bring that up is that although it looks like it's positive, in truth we don't include that in there because it's not a value for which the derivative is greater than or equal to 0. It doesn't exist technically there. And some might argue, but for the moment I'm going to stick with this one and use it. So in our particular case, this function f is strictly increasing for all the places where the function f is getting bigger, has positive slope. So looking at our picture, it looks like it goes from there to there, and it goes up from there to there. So for strictly increasing, we would say, if I was using inequality notation, I'd say that it was for x less than negative 3 and negative 3 less than x less than negative 2. That would be my strictly increasing. As a note, small differences here. If we were saying where is the function just plain old increasing, which isn't what the question asked, keep that in mind. This isn't what we were asked to do. I'm just pointing it out. If we were asked where the function f was increasing, then our differences here would be very small. We would say that x is less than negative 3 and negative 3 is less than x less than or equal to negative 2. So the only difference is actually right there at or equal to negative 2. Because at this point, if we drew a tangent line, aside from the fact that I have trouble drawing, our slope would be 0, our tangent line would be horizontal. So in increasing, just plain increasing, we include that. If it's not plain increasing and strictly increasing, we do not include that zero slope spot. Likewise, moving to the green, if we want to talk about where the function is strictly decreasing, it just reverses the signs of what we're looking for. Decreasing, we're looking for a negative slope or a non-positive slope. So our function is strictly decreasing. Well, let's see. Function's clearly decreasing from here to here, but at x equals 3, it looks like we've got kind of that's a bad one. We've got a bounce. We've got a horizontal tangent line right in the middle, but that slope is 0. So for strictly decreasing, we can't include that. Instead, we'll have x values between -2 and 3, and then we'll also have all the x values greater than 3. On the other hand, just like we did before, had we been asked instead to talk about plain decreasing or classic decreasing, it's getting smaller kind of thing, then the technical definition says that we don't have to worry about the 0 that falls at x equals 3, and we can just say that it's decreasing for x greater than -2. So basically, small little piece, like not a huge thing, not something that's probably going to burn you, but I think it's important to get that definition as fully correct at the beginning. Know that typically I'm going to ask you where it's strictly increasing or strictly decreasing, but there it is. Got a couple more of those to look at, but everything looks good. Okay, our next question is focused on number 5. And in this section, this is where you're doing kind of the traditional analysis work. You're checking whether a function is strictly increasing or strictly decreasing, and then you're classifying any of the critical numbers as either corresponding to a local maximum or a relative maximum, a local or relative minimum, or neither of those two things, while justifying your answer. Oh, excuse me. No, it might be tough to get through this one. I'm starting to feel the exhaustion of not sleeping. Okay, in looking here, question number 5. We're asked to do a whole bunch of stuff. Let's just kind of start with the classic. If we're looking to analyze this function, it's important to just kind of get out there and start looking at the derivative, because that's where most of this analysis comes from. So what I'm going to do, I'm looking at a polynomial. I'm just going to quickly compute the derivative of that polynomial. I'm going to have 1/5 of 5x to the 4th, which is just x to the 4th. Actually, I'll do this the more formal way. 1/5 times 5x to the 4th. We'll have -4/3 times 3x squared, and then plus 0. And simplifying what we have, we get x to the 4th minus 12x squared. So there is our derivative. Now again, this is a polynomial. I guess I probably should have even noted that at the very beginning. We have a polynomial, so continuity and differentiability are built in. So nothing to stress about there. But for the point here, if we want to continue progressing through here, we need to figure out where the function is increasing or decreasing. And that requires us to use the critical numbers. So to get our critical numbers, change the color each time here. To secure those critical numbers that are, so critical for us to proceed forward, we need to factor this whole thing out, our derivative out, and set it equal to 0. So I'm going to pull out an x squared. We're going to have x to the... Oh, geez, it's not 12x squared. Geez, why didn't someone tell me? What's wrong with you guys? Help me out a little bit. Come on. It's supposed to be 4. It's supposed to factor nicely. There we go. So, after doing our work properly, we'll be able to factor out GCF of x squared, and we'll get x squared minus 4. And there's lots of ways to break this up, but I'm just going to leave it exactly as it is right now. Because at this point, I can now see our critical numbers are going to be any values that make this slope, x squared quantity x squared minus 4, 0 or undefined. And since it's a polynomial and there's no place where it's undefined, we're going to have critical numbers of x equals 0, x equals -2, and x equals +2. So there are critical numbers. There are 3. That means we're going to be responsible for determining whether we have a relative maximum, relative minimum, or neither at each of those x values. Okay, now that we have our critical numbers, the critical numbers will allow us to start to analyze the function. And there are a couple different ways to do this. I'm going to try to demonstrate both a little bit as best I can. But I think the cleanest one is that technique that we're using today and demonstrating today, which is called the sign chart. Yeah. Oh, I apologize. Of course, I'm spending my summer making videos for you, so maybe I don't have to apologize. Okay, so if we have x values, we want to compare them to the derivative values, because what a sign chart checks is whether or not your slope is positive or negative. If it's positive, we know the function is increasing on that interval. If it's negative, we know it's decreasing on that interval. So in our case, we have 3 separate critical numbers to plug in, or to build our table around. So I'll put each of those values in. And then we already know that g prime of x is equal to 0 at each of those coordinates, because that's literally how we found them a second ago. So it's just straight up using it. From there, again, some people choose not to do this, but I'm going to do it. What the heck? I'm going to put the intervals we're talking about here. So this interval will be all numbers from negative infinity to negative 2, this one from negative 2 to 0, and this one from 0 to 2, and finally the last one from 2 to infinity. With those numbers in place, I now want to plug them into the derivative. So for each of these things, I'm going to be plugging into x squared minus 4. I'm going to do that work down below. But keep in mind what we really want to determine here is what is the actual slope at that point. Is it positive or negative? So we want the sign, hence the name sign chart. In order to test, we can't possibly test every number that's smaller than negative 2. So instead what we're going to do is we'll pick one number that's representative for all that region. So for instance, I'm going to plug in negative 10. Between negative 2 and 0, I'm going to plug in negative 1. These are kind of our test values. From 0 to 2, I'm going to plug in 1, and from 2 to infinity, I'm going to plug in 42. Pretty standard choices for where I'm at, but again, you may choose different numbers so long as they actually fall in the correct interval. After this, the portion that's down here, the portion that sometimes kind of messes with people, is like, well, how do you know what sign to put in there? So in order to do that, what I do is I take my number, my test value, and I plug it in, usually just mentally though, I plug it into my derivative. So in a sense, what I'm doing in my head is I'm taking negative 10 squared and then negative 10 squared minus 4, and I'm trying to see whether that is positive or negative. Most of the time though, what you'll see me do is I'll just kind of slide through some steps and focus only on the sign. So for instance, if you take a negative number and square it, you get a positive number. And if you put in negative 10 squared is 100, minus 4 is 96, that's positive also, which means the slope is positive there. So you can literally reason your way through and determine what that sign happens to be. Likewise, we can do the same thing with negative 1. So if we put in negative 1, we'll have negative 1 squared times negative 1 squared minus 4. Looking at slopes or signs, it's going to be positive. This will be 1 minus 4 is negative, and a positive times a negative is negative. Moving over to 1, we'll have 1 squared. We'll have 1 minus 4. That's going to be positive times negative again, which means it's negative. So interestingly enough, the sign didn't change in the derivative g prime. And then last but not least, if we plug in 42, we're going to have positive, and then 42 squared is a large number. Minus 4 is still large and positive. So we'll get positive at the end. So with this in mind, we're prepared to actually state the strictly increasing and strictly decreasing part. So we can say something along the lines of g is strictly increasing. I don't know really good abbreviations for some of these things yet. So g is strictly increasing for, well, we're looking for strictly increasing, meaning that the derivative is strictly positive, not 0, positive. That happens twice. So it's strictly increasing for x values on negative infinity to negative 2, as well as 2 to infinity. If you're someone that likes the explanation or the justification why, our justification here would be simply because g prime of x equals 0. And so that was our first move. Our second move would be to look at strictly decreasing. And it's strictly decreasing for the middle section. So it's when x is between negative 2 and 0, as well as 0 to 2. And again, our reason, not that hard to dissect or break into. It's going to be because g prime of x is less than 0. And I found another mistake. I apologize. This is supposed to be greater than 0. So there is our first part of the answer. You can say that this is the answer to part A. I'm not going to lie. And then second, that next brings us to the task of classifying each critical number as corresponding to a local max, local min, or neither. So we already said our critical numbers are negative 2, 0, and 2. So we want to classify each of those. And in looking up at my table, although I'm going to be using the first derivative test to make my justification, I can actually decide what we have just based on drawing a picture. So we're looking at g prime down here, which is kind of like saying what the slope of the graph is doing. And in this particular graph, our slope is positive first and then negative afterwards. If we picture what that looks like, positive slope means the function's increasing. Zero slope at negative 2 means it's down to 0. And then negative slope means it's negative afterwards. And now, of course, we know that this could look more like this, or it could do lots of things. It could be super tall and then come back down. But for the most part, all we're looking at is a representative shape. So from there, we change from positive to negative once. That tells me we're going to have a maximum. You can literally see in my picture that's a maximum. When I go from negative 2, 0 to 0, 2, I see that my signs go from negative to negative. What that means is that we're going to have neither at this point, because what's actually happening, actually I don't need to write that in there, what's actually happening is our function is negative in slope, so it's decreasing, then it flattens for a second, and then it continues decreasing. So in this case, we'll have neither. And then finally, in the last one, we're going negative slope to positive slope. That looks like a minimum. Finally, then, to wrap all this stuff up, we just have to state all these things, which unfortunately this one's a little bit long, but it brings up just kind of a little bit of everything. So first, f has a relative or local maximum. And typically we accept abbreviations of max for maximum and min for minimum, but, consult your local mathematician. So f has a relative max at, we said x equals negative 2, and our reason has to do with the pattern of sign change in the derivative. So our reason would be because g prime of x changes, and here it's specifically from positive to negative. And I hope you'll forgive me for not writing positive or negative as words and just using the symbols. I'm exhausted. So that gave us the relative max. So if you were looking for relative maxima, we're your guy. Next, we want to look at what happens if we're looking for relative minimum, or minima. So in fact, I'm tempted to just copy this entire thing, but whatever. So f has a relative, in this case, minimum. So I'll put in min, and it was at x equals 2. And our reasoning is because, let's see, so we're looking at the relative minimum. It's because g prime of x changes from negative to positive. Boom. Oh, shoot, that's not even the end. Jeez. These questions, when done fully properly, take a long time. Okay, our final piece. We've got critical numbers at negative 2 and 2 both covered. We have not talked about x equals 0 yet. So in this case, at 0, so f has something. So at 0, our graph goes from negative to more negative. Well, we talked about that earlier. That's going to represent what Franklin we typically call a slide, but for us it just means that there's definitely no maximum or minimum there. So in this case, we'd say f has neither at x equals 0. And then our reason, this is one of those reasons to just kind of commit to memory and get stuck in your head. Our reason, f has neither at x equals 0, is because f prime of x, the derivative in other words, does not change signs. And of course it does not change signs. It does change signs in other places, but it doesn't change signs there. And with that said, there is the work that we were aiming to do. I probably didn't need to box that first one, but there it is. So that's the technique that you're going to be approaching with. This is a classic kind of mid-level, middle easy first derivative test kind of question. Checking increasing, decreasing, checking maxima or minima, and then justifying your answer. Okay, that next brings us to a question from the same section. In question number 7, the difficulty comes from just having a much harder function. We don't have a polynomial anymore, where differentiability and continuity are both guaranteed and are covered really nicely. So in this case, we have to be a little bit more conscientious as we work our way through and make sure we know what's actually happening. And, really important, we know what's a critical number and what's just a number that's really important to use to break up and construct our sign chart. So in our particular case, if you can sketch this function, you might be able to do this work a little bit faster otherwise. But if you're not 100% sure what this function actually looks like, that's okay. We can construct a sign chart and cover everything nicely. So our first move, of course, is to figure out what the derivative is equal to. So we need to figure out what f prime of x is. Looking at our function, I'm thinking quotient rule. I know it doesn't have to be. Like, there are other ways that you could do this, but it'd be a pretty complicated chain rule problem if we did it in another technique. So I'm just going to do it using quotient rule. Low d high, the derivative of 6 is 0, but I'll just leave it there for a moment. Minus high d low, the derivative of x squared minus 7x is 2x minus 7, all over low, low, quotient rule. Okay, so there's our stuff, there's our work. We still have to simplify it a little bit, but you heard me mention earlier during the song, during my musical interlude, that the derivative of 6 is 0, and that's very true. What that means is this first term of the difference quotient is 0, and we're left with just plain negative 6 quantity 2x minus 7, all divided by x squared minus 7x squared. So there it is. And in fact, if you like, you could even rewrite the denominator as 2-factored squares. There we go. So this is our function f of x. It's exactly what we're looking at. It contains no less information than the previous one did, in fact. Our problem then, though, comes up next of figuring out what are the critical numbers of f of x. As opposed to just the critical numbers, I guess, themselves. So the critical numbers of f of x, those are places where f prime of x equals 0 or undefined. And so in your mind you start to go, oh, well, if undefined is allowed, then that means I can include this and that. But remember, it's also required that the function value has to exist with f of x existing too. So just kind of keep that in the back of your mind. So in looking here, if we set this derivative equal to 0, so f prime of x equals 0 at, well, the numerator would be what produces that. It would be when 2x minus 7 equals 0, which tells me x is equal to 7 over 2. Likewise, the derivative, f prime of x, is undefined. F prime of x is undefined at two other values, specifically the two vertical asymptote values of x equals 0 and x equals 7. So it is critical. It is critical and important for you to realize that the first value we found, x equals 3.5, is a critical number because it's literally a part of the original function. If you put 7 over 2 into this function, you get something that's kind of wonky looking, but it definitely exists. Here, if you plug 0 or 7 in, you're going to get 6 divided by 0 or 6 divided by 7. And even though we might be able to tell in the limit what's happening there, we don't actually have the ability to construct it the same way and actually have potentially two characters at the end of a movie interact with each other. So in this case, we have three values that are important. In fact, I call these in the problem set solutions and hopefully the lecture, I call these critical. And I call these still important values. I wanted to call them nevertheless still a little important values, but I couldn't get a good acronym attached. So with those two in there, what that means is, again, if you're not sure how to sketch the function, you can draw a sign chart and work through from there. Again. Okay. So from here, we want to look at f prime of x. We said we need to break it apart at three values. We have x equals 0, x equals 7 over 2, and x equals 7. By the way, I'm going to remind you right now as I'm constructing these tables, if at any point you're not sure which value falls where in the table, make sure you spend a moment trying to figure out where those values are. Because if you don't, you're going to run the risk of completely and totally invalidating, your table's not going to make any sense. It's reliant that we go consecutively from left to right. So be careful. So, and in our table, it's our first one I think that we've run into this with. 0 and 7 are undefined due to vertical asymptotes. So I'll just make that note. Otherwise, what we're responsible for is figuring out the sign of the slope from negative infinity to 0, 0 to 3.5, 3.5 to 7, and 7 on to infinity and beyond. So in looking here, once again, I want to pick some numbers. I want to plug in some numbers and work from there. So let's go with -1, let's go 1, let's go 5, and let's go 42. And let's just see what happens to the function. So that was a good way to go. And again, we're looking at the derivative here. So with -1, if we punch that in, we'll have -6 times -2 minus 7 is another negative. In denominator, everything's going to be positive though, because we have two things being squared. So in squared things, unless they're imaginary, are always positive. That means the slope is actually positive on this side. Likewise, if we put in 1, we'll get -6 times 2 minus 7, which is negative, all over something positive, which gives us a positive. Am I sure? Yes, I'm positive. Next, we're at x equals 5. If we plug that into this expression, we're going to get -6 times 10 minus 7, that's a positive, all over positive. We get negative times positive is negative, over positive is negative. And then last but not least, if we plug in 42, we'll have -6 times 84 minus 7. Yeah, totally, that prank on me totally backfired. So in here we'll have positive, it's all positive in the denominator. And then this becomes negative times positive is negative, over positive is still negative. So given that information, we now are ready to draw our conclusions. We have that this function is strictly increasing. I'm going to start abbreviating increasing INCR. It's going to be strictly increasing for -infinity to 0 and 0 to 7.5 or 7 halves. And although it didn't ask, our reason would be because f prime of x is positive. We can likewise talk about the strictly decreasing. And it's going to be strictly decreasing for 7 halves to 7 and 7 to infinity. And the reason is because f prime of x is less than 0. So that answers part A in a sense. I don't think I even marked that on my assignments as A or B. So there's part A. The second part looks like it's going to take a little while, specifically because we're asked about classifying each critical number. But remember, the only critical number we have in here is actually at 7/2. The other ones are just important numbers. They're vertical asymptotes and discontinuities, places where the derivative won't exist, that will break up and potentially change the sign of our expression for the derivative. So for our purposes, though, we're looking for places where the point exists and our derivative changes signs. So looking here at 7/2, we go from positive slope so that f is increasing to negative slope so that f is decreasing. That looks like a relative max, be it a cousin, an uncle, or a brother or sister. So with those pieces in place, all we can say is that we have a relative, I'll write local this time. We have a local max at x equals 7/2, or 3.5. And our reason for this one would be because f prime of x changes, because again, that's how we can tell there's an extrema, is it changes from one behavior to the other. In this case, it changes from positive to negative. And with that said, although again I didn't label it very correctly, we can just say that is part B, and that is in the books. And now for a second, just because we're here, let's do a quick little investigation and see if this actually does work and agree with what we have. So I'm going to cover up our work for just a second. I apologize. Then I'm probably going to take a quick little power nap because I'll make it through this. Okay, so just a quick little look. Let's just see if this looks reasonable for our function. So doot, clear out the MVT work we did. This is 6 divided by parentheses x squared minus 7x. So, and let's go zoom 6. Okay, it's not the best picture in the world, but not an awful picture either. Taking a look here, I'm just going to bring it over and blow it up a little bit. Okay, so there is our stuff. I want to run into my head here. There's our stuff looking at. It looks like the function is increasing, increasing, then decreasing, decreasing. Second, it looks like there is a vertical asymptote right there. Actual verticality may vary. And then it looks like the only maximum is right there, where we get kind of that behavior. So it looks to me like we've done everything correctly, and we've worked our way through a, an upper difficulty level analysis question. Okay, that brings us to our next question, now that I'm back a little more refreshed. And in this question, I'm not going to do the full problem. I'm actually going to skip part B of question number 8, but I'm going to look at part A, or at least set up the the sign chart, because I think the sign chart is actually the most difficult portion of this question. So in this case, our function is h of x equals x over 2 minus cosine of x, and we're explicitly told to focus our attention on 0 to 2 pi, so that we're only looking at one cycle around the unit circle. So in here, a good place to begin, as with all of these, is to take the first derivative, so that way you have something to start analyzing with. When you differentiate this, the derivative of x over 2, you don't need the quotient rule. That's the same thing as 1/2 x. So I can write this as 1/2, since that's linear, and then minus the derivative of cosine, which is a negative sign. So I'm going to write this as minus a negative sine of x. So in this case, we have our derivative. It's 1/2 plus sine of x, and we are looking to set that equal to 0. When we do, that leaves us with the critical numbers coming when sine of x equals negative 1/2. And a quick little look at this trigonometrically. We want sine, so we're in quadrants 3 and 4. And since we want opposite over hypotenuse to be 1/2, that means we have 30-degree reference angles, and it means that our critical numbers are going to be the two 30-degree or pi over 6 reference angles over there. So specifically, we're going to have 7 pi over 6 and 11 pi over 6. Now this actually poses some unique challenges, so let's get things set up and start to look at it. So here we go. I'm going to set up a table, or a sign chart, excuse me. Having to change my terminology. I used to call this like a interval table or something. I think that's what it was called when I was in high school, and changed a little while ago, so I'm going to be as accurate as possible. So we're setting this up. We're going to be finding the sine of h prime of x, the derivative of h, so we can do our normal analysis and eventually the first derivative test. So I want to break this up at, let's say our two values were 7 pi over 6, and the other one was 11 pi over 6. So that way our two criticals are in there, and in fact the derivative at each point is 0. That's how we constructed it. And now for the intervals in the other portions, we're going to have this running from, let's see, 0 to 7 pi over 6. We'll be running from 7 pi over 6 to 11 pi over 6 in the middle, and then finally 11 pi over 6 to, awkwardly enough, 2 pi. So in our attention, the hardest work is going to be done right over here, but for the moment, let's just play along and focus on the first two intervals. So as we dig in here, if we're going from 0 to 7 pi over 6 and we want to test out the sine, we want to pick a nice simple value to plug in here so that things come out and clean up pretty nicely. So between 0 and 7 pi over 6, which is literally all the angles from here to here, I'm going to pick the cleanest one, which for me is going to be pi over 2. So if I take pi over 2, that means h prime of pi over 2 is going to be 1/2 plus the sine of pi over 2. That's the same thing as 1/2 plus 1, which is clearly positive. So that means the derivative is positive in that first section. So going into middle, if we want to go from 7 pi over 6 to 11 pi over 6, in other words, from right there to right there, I can see that we've got one quadrantal in the middle, specifically 3 pi over 2. So in this case, we're going to have 1/2 plus sine of 3 pi over 2. It's going to be 1/2 minus 1, which is clearly negative. It's literally negative 1/2. So we're positive, then negative. Now some people just automatically go, yee! And then they put in the plus sign automatically because they think it alternates. But remember, we've seen some examples where the sign does not actually alternate every time. Now this isn't one of them, but set that part aside. So in here, the difficulty lies in the fact that we don't have an angle, a traditional angle that we can plug in that falls between 330 degrees and 360 degrees. So people struggle with figuring out, well, what can we choose? So in here, there's a lot of different ways to go. In my mind, I sort of choose a number that's a little bit like 11 pi over 12. It's some number that falls, and here I'll even facilitate this a little bit more. It's some number, if this is our 30-degree reference angle, I choose an angle that's right in here. So actually close enough. So basically this is the angle that we're going to look at because we're going all the way around to right there. So in looking at this, as we start to look at our values, of course we're going to be calculating 1/2 plus the sine of our angle. And in fact, here we don't even really have to think about 11 pi over 12. We just have to think about it as that angle theta. So in here, if this is our angle theta, the sine value, if we look right here, that sine value is -1/2. Down here, the y value, or the opposite over hypotenuse, is clearly smaller because this value doesn't go as far as this value would. So basically that's a lot longer. The shorter one is what we're looking at. So what I'm going to say is this is something smaller. It doesn't really matter what it is, it's just got to be smaller than -1/2. So I'm going to call it -1/4, because why not? We're saying it's the angle theta. We can say that's the angle theta in that quadrant whose sine is -1/4. The reason that works then is by recognizing that sine is smaller, we can look at this as 1/2 minus 1/4, and then we'll know that this is 1/4. Or more importantly, whatever angle small value we choose, we get a positive number, which means this is in fact positive. So again, I think that this is the most challenging part of that question. If I were writing it for a test, I probably wouldn't choose to use 30-degree reference angles. I'd choose 45 or 60. But at the same time, it's good to have thought about it once, and I figured it would be helpful to clarify a little bit what I'm doing. Again, basically what I do is I choose an angle. Don't even choose what the exact angle is, although I tried at the very beginning, you saw. Choose what that angle is. I recognize that the sine value is smaller than the original angle that we were looking at that had -1/2, and that allows me to figure out what the sine is and determine the rest of the sine chart. And with that said, as I told you, I'm not going to do all the normal work. The rest of this follows straight up from what was there before, strictly increasing, strictly increasing, strictly decreasing. We have a maximum and a minimum, which, sine curves do that, so that seems pretty fair. Nothing really fancy there for us to do otherwise. So there is question 8. At least we did the setup for it that I think was the hard part. You can finish the rest of it. Okay, next, that brings us to question number 10. And once we get to this section, this is where some of the more challenging portions of the overall assignment come up. Things where you have to think about meanings of different pieces. And in question number 10, I'm only going to focus on 10b and 10c, which I believe are the clear, harder problems of parts of this problem. So first of all, what does our problem say? It says the function f of x is strictly increasing for x less than 5 and strictly decreasing for all x greater than 5. So right off the top, what I'm going to do first is I'm just going to draw a picture for this. And again, some people would disagree, but again, all we know about f is that it's got to be increasing when we're smaller than 5, and then decreasing when we're larger than 5. So in a sense, that's what I know is happening here. With that in mind, my next move is to start to look at where certain transformed versions of the function are actually increasing or decreasing. So in part B, we're asked to find the intervals on which h of x equals -f of x is decreasing. So right away, the first thing I'm going to do is I'm going to take the derivative. So if h of x equals -f of x, h prime of x is equal to -f prime of x. So keep this in mind. If f is strictly increasing for x less than 5, that means f prime is positive for x greater than 5. And then if it's strictly decreasing for x greater than 5, I might have said that last one wrong, I apologize. That means f prime of x is negative when x is greater than 5. So with that in mind, we now have to think about what's happening. So if we're taking that derivative from before and we're multiplying it by a negative, then f prime being positive, so here we'll do it this way. If f prime of x is greater than 0, in other words positive, then f prime or negative f prime of x is negative. Excuse me. That makes sense, right? Again, we're just taking some of those positive before, multiplying by a negative, that makes it negative. Therefore, since f prime of x is greater than 0 for x less than 5, h prime of x, which is equal to -f prime of x, is less than 0 for x less than 5. Right? Because all we're doing is multiplying by a negative sign. Therefore, h is strictly decreasing for x less than 5. And if you're looking for the justification, I just did my justification up here. I reasoned out what was true about our function's derivative, our function being h, its derivative, by relating it to what we knew about f prime. And another way to look at this is if we look at it graphically over on the side, another way to just kind of confirm what we're talking about here, is if we take this as f of x, and we want to instead graph negative f of x, think about what happens. All that happens is the entire graph flips. So instead of being up there, we end up with this shape. And therefore, if we're looking for where negative f of x, also known as h of x, is decreasing, that's now over here. The same values for which f was increasing. So again, very little like formal work here. There's not a lot of algebra here, although I think this step is really an essential component. Like if I were grading this problem, that'd be something I'd be looking for in addition to the rest of it. But the idea is simply like what happens to the derivative and then thinking about what that implies for strictly increasing and strictly decreasing. Okay, similarly, but a little bit more challenging. It wants us next in part 10c to find the intervals on which k of x equals f of x minus 11 is strictly increasing. So in this case, I'm going to start in the exact same place. K prime of x is going to be equal to f prime of x minus 11 times the derivative of x minus 11. But you probably already realized that x minus 11's derivative is just 1. So that means that k prime of x is just equal to f prime of x minus 11. So now, with that said, we've got to think about some other things. So in other words, we need to think about how this connects to f prime. So if f prime of x is what we're looking for increasing, is greater than 0 for x less than 5, then f prime of x minus 11, so this is kind of the big spot, f prime of x minus 11 is greater than 0 when its argument x minus 11 is greater than 5. Right? Because all this is doing is shifting it around. So with that said, that's the same thing as saying x is greater than 16. So therefore, k is strictly increasing for x greater than 16. So in a sense, what this one did was it took into account horizontal shifts, or simple transformation. So stealing one more time our picture from before, if this was our picture in the past of f of x, we'll call this f, then f of x minus 11 is just going to be the exact same picture, but the difference is here, we're going to take the, let's do this correctly, take everything relevant, now it doesn't want me to, whatever, and we're going to shift it 11 to the right, and then down here, we are now 11 units away, which means that we're now at 5 plus 11, or 16. And in fact, if you wanted to, you could pick a function that is true in this way. There's lots of good functions that work this way. And you could actually like play with a real function and prove all these same things. But just thought this was a good introduction to the problem. But you know what, since we're here, let's go take a look at Desmos really fast and see if Desmos does in fact agree. We'll pick a function that works this way, Desmos. Okay. So quick little look here. Let's fix what Desmos looks like. Ooh, that's kind of cool, but not for now. Play with that later. So we said that it was increasing for x less than 5. So I'm going to go negative quantity x minus 5 squared. So yeah, there we go. And actually, let's just add a bunch up here. Plus 4. Okay, so the question I'd ask you is, first and foremost, does this apply? So we were supposed to find a function that was strictly increasing for x less than 5 and strictly decreasing for x less than 5. So if that's 5, strictly increasing, strictly decreasing. So our first question to ask ourselves was, well, what happens when we deal with negative f of x? I think we had h of x was equal to negative f of x. Well, look at that. Strictly decreasing for x less than 5. So our work in 10b was correct. Finally, we had k of x equals f of x minus 11. So our question is, does this work also? I think we came to the conclusion that k was strictly increasing for x greater than 16. I say greater than, I think I was supposed to say less than 16. So let me go back and see, I think I did. So in this case, we wanted it to be strictly increasing. That is definitely x values less than 16. So in fact, it's a good thing that I checked, because I actually reversed my sign here. So clearly the increasing portion of this, let's fix this. clearly the increasing portion of this. Here, I'll do it this way. Hey, look at that, literally correct sign, incorrect sign. Let's fix this. So these are both supposed to be flipped. X minus 11 less than 5, so x is less than 16. And then right here, quick modification for x values less than 16. So as it turns out, our work was correct, our conceptual idea was correct. I just flipped a sign accidentally, and in my decreased state, wasn't able to catch it. So apologies for that, but hopefully this clarified what question 10 was asking you to do a little bit. I feel like it's probably a multiple choice kind of question if it shows up on an exam, for what that's worth. Okay, next, this brings us to question 11, and I've chosen to do only one of the two parts of question number 11, because I think really if you can do 11b, if I can kind of clarify things for you on 11b, then you'll be able to simply work through 11a. So here we go. So first of all, in question 11, we are told that g of x is a strictly increasing function for all x. So before we do anything else, it's worth pointing out what that actually means. If g is strictly increasing for all x, that means that g prime of x is positive, aka greater than 0, for all x. So that's really important. In a sense, it means that g prime of anything, doesn't matter what you put in there, you can put in g prime of Cookie Monster, and g prime is, or sorry, I should write it as g prime of anything is positive. So any number you put in there, anything's fine. I guess Cookie Monster's not a number, but you know, it's been a while since I watched Sesame Street, so who knows. So the important thing is g prime of something is positive, no matter what we put in there. So keep that in mind now. The question next says, let k of x equal g of x squared minus 6x, and it wants us to find the intervals on which h is strictly increasing and justify our answer. Well, if we're talking about increasing and strictly increasing, that's a code for find the derivative and use it to tell me stuff. So let's take the derivative here. We want to find k prime of x. To do that, we need to take the derivative of g of x squared minus 6x. In fact, I'll even say that. It's going to be the derivative with respect to x of g of x squared minus 6x. And what that means is we're going to need to use the chain rule. And although I've been moving pretty fast through differentiation in this problem set, I'll do this carefully once. So I'm going to let k of u equal g of u. I'm going to let u equal x squared minus 6x. Then k prime of u is going to be g prime of u. This is standard chain rule stuff. U prime is going to be 2x minus 6. And if we want to get k prime of x itself, that means we're going to have to do g prime of u times u prime. More importantly, we can write that as 2 quantity x minus 3, g prime of x squared minus 6x. So there is our derivative. And at first, this expression looks pretty darn complicated. And more than that, you might be asking, well, how am I going to know where that's positive? And the answer, of course, is that this isn't actually going to be very difficult. So for the sake of clarity, let me create a sign chart here really fast. And then afterwards, we'll go to Desmos and clarify some things as well. I think that'll be a nice little capper for it. Okay. Oh, good. It worked that time. Okay, in our piece, we want to talk about k prime of x. And of course, k prime of x, we just said, is 2x minus 3 g prime of x squared minus 6x. Yeah? Okay. Okay, so there's our stuff. So our x values here. The first thing we want to do is we want to figure out where are all the critical numbers of this. So if we set this equal to 0, the question might be, well, when does this equal 0? Well, obviously, that's going to mean that we have one critical number at x equals 3, right? Because if you plug in 3 here, you'll get 2 times 0, 3 minus 3, times something. Second, you might ask yourselves, well, are there any more? And the answer is no, because the other two factors, g prime of x squared minus 6x, does not equal 0, because it's positive. It's automatically greater than 0, so it's never going to equal 0. And of course, 2 doesn't equal 0 either. So the only thing that's going to be critical for us is going to be x equals 3. So that's a huge lift. It means when I set up my table, I'm just going to have to break it apart at 3. And of course, we know k prime is going to be 0 there. And then we'll look at x values less than 3 and x values greater than 3. So with that in mind, again, hopefully everything's clear there. I'll recap once more before I finish this off. So what have we done so far? We took the derivative because we were talking about the increasing or decreasing property of k of x. We took the derivative using the chain rule. With that chain rule, we got an expression that looked pretty crunchy, but when we thought about it, the only factor that contributed to this sign was x minus 3, because g prime of anything has to stay positive. And of course 2 is automatically positive. So let's use that information. Putting in a value less than 3, let's put in 0 for instance. It's a really good test value. Well, think about what the value of k prime of 0 would be. We'd have 2 times quantity 0 minus 3 times g prime of 0. And again, this can be kind of awkward the first time you do it, but let's think. 2 is positive, 0 minus 3 is negative, and g prime of 0, well, g prime of 0 must be positive because g prime is positive for all x values. So that means g prime of 0 is positive as well. A positive times a negative times a positive is negative. On the other side, if we plug in a different value, actually I'll keep the same ones. Let's plug in one of my favorite numbers, 42. Nah, it's so big, I don't care. This will then be 2 times 42 minus 3 times g prime of 42 squared. 42 squared minus 6 times 42. Well, 2 is positive. 42 minus 3 is 39, which is positive. And g prime of some number, it's a big number, but it's a number, is positive as well. Because, of course, g prime of x is positive for all x values. That means a positive times a positive times a positive is positive. And of that, I am positive. And given that information, we're able to finish up this problem and state that k of x is strictly increasing for, what do we say? X greater than 3. And our justification is really all of the work we've done up to that point, but you could say something kind of snarkily simple, like because k prime of x is greater than 0. And I would argue that that's a really good finishing piece because of the fact that we've done all that justification and explanation up top. So with that in mind, this feels a little bit weird. This is kind of abstract function working. And that can be kind of challenging, I admit that. And the first time I saw this question, I found it to be kind of challenging, and I ended up doing kind of the same work, but I didn't really know where I was coming from. What was interesting the first time I did this work is that I actually had a student who did it in a completely different way. His name was Mighty Chen. He was in theater. He was one of the huge brainchilds behind Lake Calc when we did that music video in BC in the class of 2016. Favorite number is 37. But what Mighty said when he ran into these problems was something I'd never seen before. He just went, okay, let g of x be a strictly increasing function. I'll make one up. And then he reasoned his way through the rest. So let me show you what Mighty's method would be. So first and foremost, what Mighty did was he picked a function that met that criteria. So he called g of x an always increasing function. Can you think of a really easy always increasing function? Because he did. He thought of x. Would you agree that's always increasing? Yes. Yes, as that ventriloquist dummy behind me just said, yes, it should be right. That is always increasing. The derivative is positive everywhere. So with that in mind, the question we asked was about where k of x, which was equal to g of x squared minus 6x, was increasing itself. And looking at our picture, we can see very clearly that g is increasing when x is greater than 3. So, and again, it didn't matter what he chose. If he chose any function that was always increasing, he could choose 2x plus 3. Notice once again, it's always increasing. It doesn't matter. Or it's always increasing for x greater than 3. So his key was figuring out that that was the trick, was that if you find a function that represents that thing, since it's true for since g isn't specified as this particular function, if something is true for g of a particular strictly increasing g of x, then it must be true for all of them. And so he reasoned from a very simple function and was able to get the correct answer as well, particularly in a multiple choice kind of world like this one was. So if the first explanation didn't do it for you and you felt like it was too conceptual, cool, there's other methods out there. The Mighty Chen method would be a perfectly good one as well. Alrighty. Finally, this brings us to the last question of the assignment. In this last question, which I've designed specifically to mimic the types of questions that I ask on this Unit 3 exam, like usually it's one of those last free response style questions, what I've done is I brought together some function analysis along with differentiation. It's just a good opportunity to check to make sure that you can still differentiate with all the techniques that are out there. And you've seen I sprinkled in chain rule and things throughout this assignment too. There's also a quotient rule earlier I want to say. But this is a really good opportunity to do it in a very simple, straightforward, and easy to compute way. So first of all, 12 itself begins with that announcement. Let f be a twice differentiable function. And of course, in a previous assignment, I think it was the last one, we talked about the fact that f being twice differentiable means that f prime is differentiable, which means f prime is continuous, which means f is continuous and differentiable as well. So there's some good information that comes from that first statement. Basically means that we can deal with any derivative that we want that involves f prime, or f double prime. From there, it says that values of f and its derivative f prime of x are given below. So those values are right over there. So we're going to use those values to reason out. First part A. Let p of x equal x cubed plus 4f of x. Is the graph of p of x increasing, decreasing, or neither at x equals 1? So what this is telling me is if we're asking about whether p of x is increasing or decreasing, what we want to know is the sign of p prime of x. So to get there, what we need to compute first is p prime of x. And typically, when this kind of question shows up on an AP style or an AP free response question, what we'd be looking for first is, did you compute the derivative correctly? So in our case, our job is to differentiate with respect to x cubed plus 4f of x. So that's not a particularly difficult expression to differentiate. The derivative with respect to x of x cubed is 3x squared. And the derivative of 4f of x is going to be plus 4 times the derivative of f of x, which is 4f prime of x. So there is p prime of x. So we've got the derivative itself. That's typically 1 point. Our second point then comes, typically, from figuring out what that derivative is at x equals 1. So specifically, we want to know what is p prime of 1. Well, that's going to be 3 times 1 squared plus 4f prime of 1. In other words, we get 3 plus 4 times whatever f prime of 1 is. And f prime of 1 is negative 3. So given that, we can find the actual exact value. We get p prime of 1 is 3 minus 12, or negative 9. And at this point, we know all we need. Negative 9 is clearly negative. In fact, on the last AP exam, they didn't even force you to draw that comparison at any point. But I'm going to, because that's my expectation. So given in that information, we can now say that p of x is decreasing. In fact, we could say strictly decreasing, by the way, but we'll just go with decreasing for the moment, is decreasing at x equals 1. And our reason is because what we calculated, also known as p prime of 1, is negative. And there is our answer and justification. But of course, the answer and justification is probably just 1 point. If you're scoring this one at home, which I haven't done this a whole lot, basically you'd get a point for your derivative, you'd get a point for getting the correct value of the derivative at 1, and then you get a point for the answer with justification. Very classic grading style for a very classical feeling kind of question. So there it is, part A. Simple differentiation to go through, but you're doing that full analysis here. You've just got a much cleaner context to perform that analysis. Next, that brings us to question 12b. In this case, we've got a similar setup. Let c of x equal f of x squared plus 1. Write the equation of the tangent line to c of x at x equals 5. So in 12b, there's no actual analysis. We're not doing the traditional analysis, but we're still using differentiation skills and reading through the table to fill in those particular values. So since we're looking for a tangent line here, we're going to have to do two things. First, we do need to figure out what is c of root 5. That's going to be the actual y1 value for our tangent line. And in looking up there, that's going to be f of the square root of 5 squared plus 1, which is f of 5 plus 1, which is f of 6. And reading our table, f of 6 is 1. So basically, we've got our y value automatically. We're covered. We also know, of course, our x value is root 5. That leaves us, of course, with our derivative step. We need to figure out what c prime of x is. Well, c stands for, in this case, chain rule. So what I need to do is I need to use the chain rule to compute the derivative of this expression. I'm hoping, though, that you're okay with me doing the chain rule quicker in this case. I think this is a good opportunity to point out that this is not a candidate for you to do the basic decomposition method, or the full decomposition. This needs to move a lot faster than that because the pieces are really clean. So let's think about it. If c prime of x is the derivative with respect to x of f of x squared plus 1, we can do a real easy analysis on what's on the inside and what's on the outside. So first, the outside is f, so our derivative is going to be f prime of whatever's on the inside. And then, of course, we'll have to multiply by the derivative of that inside stuff. Simplifying our pieces, the derivative of x squared plus 1 is just 2x. We get 2x f prime of x squared plus 1. Now that we have it, we want to calculate c prime of root 5. And again, I hope I didn't move through that too quickly. That's just the chain rule. But these are the problems that you should be doing in your head. You should be doing really, really quickly or with minimal work. So just being honest. So if we want to calculate c prime of root 5, it's going to be 2 times root 5. F prime of what we know will be root 5 squared plus 1. Means we're going to get 2 root 5 times f prime of 6. And pulling that out of the table, f prime of 6 is equal to 6. We get 2 root 5 times 6, which is 12 root 5. So now we have our slope. We have slope. We have our y value. We were given our x value. So we can go ahead and write out our tangent line. Line equation. Sorry, I'm singing the old tangent line song. So there is our tangent line. And in fact, in I think probably about a week and a half or so, you might even be working on finding normal lines to go along with it, which isn't that much more difficult. But again here, good opportunity to use chain rule. Call back to tangent line equations. Don't let go of those things. It's a huge fundamental thing that we're going to be doing. And of course, we had to read the table to get all our values. So there is 12b. Okay, 12c. 12c is, I think, the biggest push out of here. This one doesn't involve the full analysis, but I think it's a really important question. A good transition for tomorrow as well. Good prep. In 12c, we are told to first let p of x equal 3x f of x. So you're probably already thinking, okay, here we go. What derivative rule are we going to probably need this time? And p definitely is going to stand for product rule. You can just see it coming. This is going to be a product rule situation. Now here's where things get interesting though. It says p double prime of negative 2 equals 10. So we're talking about the second derivative here. So we're actually going to need to differentiate not just once, but twice in order to be able to deal with the rest of this problem. So what I'm going to do is I'm going to save this work for a little bit, and I'm just going to start by figuring out, actually I'll leave it there. What I want to get to is I want, or need, depending on how essential your performance in calculus is, what we need to get to p double prime of x. So that's where my focus is going to begin. Well, of course, we can't get to p double prime without first getting to p prime. So I'm going to find p prime first using the product rule. And we haven't done product rule in this assignment yet, so that's going to be the derivative of 3x times f of x plus 3x times the derivative of f of x. Pretty clean, right? That's going to be equal to 3f of x plus 3x f prime of x. Now, normally we'd stop and say, yay, look at us, we did a good job, let's plug in and find our derivative value. But remember, we want p double prime. So if we want to actually get to p double prime here, then what we need to do is we need to take the derivative of this entire thing one more time. So in other words, we're going to get to p double prime of x. In this case, the first term is just a scalar times f, so the derivative is just going to be 3 times f prime of x. But the second term is going to require the product rule. So right here, in fact, I'll change the color just for clarity's sake, I'm being as careful as I can here. This is going to require the product rule, which if I just write PR makes me think Puerto Rico. So there we go, we're going to use the product rule. So once again, we'll do this a little bit quicker here. I'll do it that way. The derivative of 3x is 3 times f prime of x plus 3x times the derivative of f prime of x, which is going to be f double prime of x. So with that said, we get to our second derivative. Combining some ingredients here, I see some like terms, specifically right there. This is actually 6f prime of x plus 3x f double prime of x. So we've computed the second derivative, and it required product rule twice, which, maybe not ideal, maybe not your favorite way to spend the day, but hey, good experience for sure. From here, our next move is, of course, to start reading the rest of the function. It tells us first and foremost that p double prime of negative 2 is equal to 10. So we're talking about p double prime of p double prime of negative 2, and that's going to be 6f prime of negative 2 plus 3 times negative 2 f double prime of negative 2. And again, in your heart, you might start to feel a little bit of anxiety because you're like, wait, I don't know what f double prime negative 2 is. But that's okay. They told us the value of this expression is all equal to 10. That's literally what they're saying right here. And they want us to find f double prime negative 2. So what we need to do now is we need to solve for the piece that we don't know. We need to figure out what that guy is. Well, plugging in our values here, we want 6f prime of negative 2. F prime negative 2 is 1. So this is 6 minus 6f double prime of negative 2 is equal to 10. Moving some stuff over, we can subtract 6 from both sides. We'll get negative 6f double prime negative 2 equals 4. And then we can divide both sides by negative 6. And it will tell us that f double prime of negative 2 is equal to negative 2/3. Actually, I'll box the whole thing. I'm proud of that. So once again, not the true analysis yet. Tomorrow we'll start to work on it because the next lecture focuses on concavity, which is analyzing with the second derivative. But for the moment, we just solved for it like it was a missing scalar kind of question. One of those old find the value of k kind of things. So from there, there's everything in there. The biggest thing to pull in here was I think that this was challenging due to the double product rule work that we had to do. But at the same time, I think this is something you're really more than capable of and something that I expect you to be able to do. So there is 12C. And last but not least, but I think I made this pretty clean, just a little bit, did the wrong color. So in 12D, once again, we moved away from the pure analysis, and we're asked to go back and call back to something that we've actually been using a little bit, which is differentiability. So here we're given a piecewise function that involves our table function, f of x, and we're supposed to find the values of a and b, which are the coefficients of two terms of a quadratic function, such that k is differentiable at x equals 6. Now, you might not be saying thank you for this, but truthfully, by specifying that I want this differentiability at x equals 6 only, I've saved us a ton of work. We don't need to talk about either other branch in any way. All we need to do is focus in on what's happening at x equals 6. So that'll simplify this question quite a bit. And since I'm doing these before I teach the course this year, hopefully that'll have simplified some things on your actual exams too. So, hopefully. So remember, in order for something to be differentiable at 6, we need k of x continuous at x equals 6. And second, we need k prime of x to be continuous at x equals 6. In a sense, this is to make sure that we have both a continuous function and that there's no sharp turn in our function itself. So each one of these is going to produce some work for us to go through. So let's do that. This isn't that bad. So if k is continuous, of course, there are three properties that are there. The function value exists, so in our case, k of 6 exists. The limit as x goes to 6 of k of x exists, and that those two things are the same. We're going to focus our attention on number 2. In other words, does the limit exist at x equals 6? And remember, since we've got this boundary situation here, what really matters is does the limit as x approaches 6 from the left side of k equal the limit as x approaches 6 from the right side of k? By the way, it's as good a time as any to point out that if you're wondering why I'm bringing up topics like differentiability and some of these things all the time, the reason is these are the small holes that I've seen in students the last few years. And since this is my first opportunity in a couple to redo all of the problem sets and to create all these videos and stuff, I think it's a good time to really make sure that I'm going back to the topics people have had trouble with and giving you as much practice and conversation and information about them. So just know that that's part of it. So the limit as x goes to 6 from the left side of k of x. Well, this is the left values. That's going to be equal to f of 6. On the right side, we're going to have a times 6 squared. I'm literally just plugging 6 into the two branches. Plus b times 6. Simplifying here, f of 6 is 1. So 1 is equal to 36a plus 6b. And at this point, we have two unknowns in one equation. We can't solve anything. But what we can do is we can now go over and talk about the continuity of k prime. So of course, if we want to talk about continuity of k prime, we first need to know what k prime of x is. So k prime of x is going to be the derivative of that function over there. We're going to have f prime of x when x is less than or equal to 6. And we're going to have the derivative of ax squared plus bx. Now keep in mind this is the derivative with respect to x. So the a and b are just scalars. So we'll have 2ax plus b when x is greater than 6. So now we need this to be continuous, which means we need to deal with the limit as x approaches 6 from the left of k prime of x. And it needs to be equal to the limit as x approaches 6 from the right side of k prime of x. Again, pointing out, yes, there's three parts to this definition of continuity. We're focusing on the limit one, which is the most restrictive. So pulling that in, this side, the left side will be f prime of 6. The right side will be 2a times 6 plus b. In this case, if we clean this up a little bit, f prime of 6 is 6. So 6 equals 12a plus b. So now we have two different equations, each with two unknowns, and that is recipe for solvability, assuming that there is a solution. So what I'm going to do is I'm going to bring these two equations together. 1 equals 36a plus 6b, and 6 equals 12a plus b. And now I want to solve for one of those pieces. I want to solve for one of the variables. And as I look in here, I think the easiest one for me to solve for, I'm going to do it with a light blue pen if that's okay. I think the easiest one to solve for is actually b first. So I'm going to multiply the second equation by -3. That will give me, of course, the same. 1 equals 36a plus 6b. Down below, I'll have minus 18 equals minus 36a minus 3b. So combining these two together, adding them up, solving the linear system by elimination, we get -17 equals, of course, we get a 0, and then 3b. It's a bad b. That stings, that's a bad b. Maybe a pun. So from there, what that means is b is equal to -17 over 3. So maybe not your favorite value of all time, it's a little bit crunchier than maybe you'd like, but that's okay. Now that we have the value, we can solve the rest of this expression. We can figure out the rest of this stuff. So now that we have b, I'm going to take it, and I'm just going to plug it into the nearest equation. I'll plug it into there. So that's going to be 6 equals 12a minus 17 over 3. And to wrap this up and to try to solve this, I'm going to multiply everything by 3, just because I think that's going to be the easiest way to do it. So in fact, I'll do this better. So that's going to give me 18 equals 36a minus 17. I'll add 17 to both sides to get 35. So 35 equals 36a. And finally, last but not least, a is 35 over 36. And of course, since I'm the one that controls the timing of this video, I'm going to go ahead and check to make sure that I can't check because this is a tabular function. It's numerically defined. Never mind. But whatever, we got the values. It's the same values I got last time when I wrote the assignment. So with that said, there is some classic differentiability work. I hope that this has cleared some things up for you and helped strengthen your understanding of the lecture, focused on the first derivative test and increasing, decreasing, relative max, relative min justification. In any event though, thank you for watching, and I hope you have a great night.